Day 122 notes, pre-calculus. Today we're going to work on solving different equations or different calculations using our trigonometric ratios. First off, in problems 3 through 8 in our textbook, we need to find the exact values of the 6 trigonometric ratios of angle theta. Now, fortunately, we've been given all 3 side lengths here. That's going to make these ratios very easy to find. What I like to do is identify the opposite side first, because the hypotenuse is very easy to find. The opposite side is always directly across from this angle measure, and that means that our adjacent side is the side that's left over. Now, by definition, our sine of theta must be equal to the opposite side divided by the hypotenuse, which is 4 divided by 5. Cosecant, by definition, is the inverse of sine. So when we have an inverse of a function, that means that we can just flip these fractions over and we have our inverse result. So if sine of theta is 4 divided by 5, then cosecant of theta is 5 divided by 4. Cosine of theta is our adjacent side divided by 5, or divided by our hypotenuse. Our secant, which is the inverse of cosine, is the inverse of this fraction, so 5 divided by 3. Tangent, by definition, is our opposite side divided by adjacent, so that's 4 divided by 3. And therefore cotangent, which is the inverse of tangent, must be 3 divided by 4. Let's try another. Here's my theta, my angle measure, and I'm going to point to the opposite side. So we have our hypotenuse, our opposite, and our adjacent sides now marked. Sine, which is opposite over hypotenuse, 7 over 25. Cosecant must be 25 over 7. Cosine, adjacent over hypotenuse, so we have 24 divided by 25. Therefore, secant of theta must be 25 over 24. And tangent, our opposite side divided by adjacent, so we have 7 divided by 24. The inverse of that is 24 divided by 7. For a problem like number 5, the angle measures again are pretty easy to find if we have all 3 sides. We're missing one side here, so we're going to have to use the Pythagorean equation to find it. Now 41 is our hypotenuse. That's the side that's opposite of our right angle. It's also the longest side here. So I know that 41 squared must be equal to 40 squared plus an unknown side length squared. Again, I know that because a squared plus b squared must equal c squared according to the Pythagorean equation. So I'll put 40 in place for a. I don't know what b is yet, and I'll put 41 in place of c. So 40 squared is 1600 plus b squared must be equal to 1681. B squared must then be equal to 81. Therefore, our missing side length b has to be 9. Okay, so we have our opposite side, we have our adjacent side, and we have our hypotenuse. So let's fill in the rest of this data. For sine, we have opposite over hypotenuse, 40 over 41. For cosecant, we have 41 over 40. For cosine, we need adjacent divided by the hypotenuse. And for secant, we need the hypotenuse divided by the adjacent side. For tangent, we need our opposite side divided by adjacent. And for cotangent, we need adjacent divided by opposite. And so now we've identified the 6 trigonometric ratios based on 3 different triangles. In problem number 9, we need to find part A, sine of alpha and cosine of beta. This is an interesting question because when we're looking at alpha, we have our opposite side length here. We have our adjacent side length here, but if I'm looking for sine, I need to utilize the hypotenuse as well, and I don't have that number. Hopefully you recognize this type of right triangle though. This is a 3, 4, 5 right triangle. The numbers 3, 4, and 5. Whoops, no, that's not going to be true here. 4 would have to be one of my side lengths down here, and 5 would be the hypotenuse. Let's go ahead and use the Pythagorean equation to find this missing side length. 3 squared plus 5 squared must equal c squared, the length of the hypotenuse. So 9 plus 25 is equal to c squared, and 34 then is equal to c squared. C by itself is equal to the square root of 34. Okay, good. I avoided a costly mistake there. Now let's go ahead and start answering these questions. Sine of alpha. So alpha is the angle measure down here in this corner. Its opposite side is 3, and the hypotenuse is the square root of 34. So if I needed to evaluate sine of alpha, I know that this is equal to 3 divided by the square root of 34. Let's see what cosine of beta is. Now beta is this side here, and its opposite side is down below. That makes 3 the adjacent side, which is exactly what's needed for cosine, and the hypotenuse is needed as well. So this is kind of interesting, right? The sine of alpha is the same as the cosine of beta. Let's take a look at some other examples here. Tangent of alpha. Well, alpha again down here, pointing all the way across, we have our opposite side and our adjacent side. So for tangent, that's the same as opposite divided by, not hypotenuse, but adjacent, so that's 3/5. Then cotangent of beta would be equal to, here's beta, cotangent would be not opposite over adjacent, but rather adjacent over opposite, which also is 3/5. So tangent of alpha is the same as cotangent of beta. And finally, part C, we have secant of alpha, secant of alpha. Now secant of alpha is the inverse of cosine of alpha. So here's my alpha, this is the opposite side. The cosine of alpha would require our adjacent side divided by the hypotenuse. But since we're dealing with secant, that would be the inverse of that. So instead of 5 divided by the square root of 34, we're going to look at the square root of 34 divided by 5. Now cosecant of beta would be equal to the inverse of sine. Now sine usually requires us to take the opposite side and divide it by the square root of 34. So if that's sine, then cosecant would have to be the inverse of that, which is the square root of 34 divided by 5. So I like this question because it calls to your attention the relationship between different types of functions and their complementary angles. So alpha and beta were complementary because these two would add up to 90 degrees. And if you take the sine of one and the cosine of the other, those two values are equal to one another. The tangent of one angle and the cotangent are the same, and the secant of one angle and the cosecant of the other are exactly the same as well. All right, here we go. 11 through 16, we need to find the side labeled x. And rather than just in exercises 13 and 14, we'll just say in all examples, state your answer rounded to 5 decimal places. So here we have our target, the x value, which is directly opposite of the given angle. So we have an opposite side, and we have a hypotenuse. So the rules that deal with opposite and hypotenuse are either sine or cosecant. I'm going to use the sine calculation here. Sine of 30 degrees must be equal to x divided by 25, opposite over hypotenuse. So therefore x would be equal to 25 times sine of 30. X then must be 25 times sine of 30. And that comes out to be 12.5. X must be 12.5 units long. We don't have to round that one. It doesn't extend past the 5 decimal places. Let's see what we get here when we're solving for this x. Now, the given angle here points all the way across to another opposite side, and x again represents our hypotenuse. So we have got an opposite side and a hypotenuse. Let's go ahead and use the cosecant rule this time. Cosecant of the angle measure 45 must be equal to not the opposite divided by hypotenuse, but rather the hypotenuse divided by the opposite side. So in this case, x would be equal to cosecant, oops, I'm sorry, let's get that 12 out there first. 12 times cosecant of 45. So 12 times cosecant of 45. That's 12 times the square root of 2, but if we want this rounded to 5 decimals, that's 16.97056. 16.97056. Let's take a look at 13. Here's our given angle measure. Directly across from it is our opposite side. We have the opposite side and our hypotenuse yet again, so we have to use the sine function. We'll have to use the sine function again because we're dealing with an opposite side and a hypotenuse. So sine of 60 degrees is equal to x divided by 13. X then is equal to 13 times sine of 60. So 13 times sine of 60 is equal to that fraction, or 11.25833. 11.25833. Now, sine isn't the only function that we could use when we have an opposite and an adjacent side. We very well could have used cosecant as well. Cosecant of 60, however, is equal to the hypotenuse divided by the opposite side. So in this case, x is equal to 13 divided by cosecant of 60. And when I complete that calculation, 13 divided by cosecant of 60 degrees, we get that same ratio, or this decimal again. X is 11.25833. So either approach for that would have been perfectly fine. And to finish out the examples for today's notes, we need to do two things: express x and y in terms of trigonometric ratios of theta. This means solve for x and y. So this is another way of saying that: solve for x and y. So let's see what it would take to solve for x. Now, what I have down here is an adjacent side, adjacent to this theta value, and I have a hypotenuse as well. So if I have an adjacent and a hypotenuse, I might use the cosine rule and I might use the secant rule. I'll go ahead and use cosine here in this case. Cosine of theta must be equal to x divided by 28. Therefore, if I was solving for x, then all I need to do is multiply both sides by 28. And 28 times cosine of theta would represent the solution for x. So that takes care of expressing x in terms of a trigonometric ratio. Now, as far as y goes, this is an opposite side, and an opposite side, along with a hypotenuse, must rely on the sine function or the cosecant function. So I'm going to call this sine of theta equals y divided by 28. When I multiply both sides by 28, I see that y by itself is equal to 28 times sine of theta. and that's now given us x and both y solved for or expressed in terms of trigonometric ratios. I hope this video gives you some exposure to different ways that we can solve trigonometric problems. If this is something that's familiar to you, then I hope that it's coming back and you're very comfortable with it. If it's not that familiar to you, then I again tell you to continue studying these trigonometric ratios. Make sure that you understand their definitions, and practice and practice and practice again these problems that we go through in the video until you get the hang of it. I'm also available before school or after school in case you need it.